The correlation coefficient provides a handy measure of goodness of fit, but we need to be careful while using this correlation coefficient to be able to decide if the fit is good or not. Because giving more meaning than what is warranted might be misleading. And just because R is close to 1 doesn't mean that the fit is necessarily good actually. So in general it looks good, but we have to be careful. We will talk about those. For example, R can be relatively high when the relationship between y and x is not even linear. So there is a study of Draper and Smith in 1981, an old study actually, and they provide guidance and additional material regarding assessment of results for linear regression. In addition, at minimum, you should always inspect a plot of data along with your regression curve. So rather than only checking R, have a plot of the data and the curve to see if it's really good for the fit or not. And as described in the next section, software packages include such capabilities. So in the next slide, we will see an example that even though R is close to 1, actually it doesn't mean a good fit actually. In this slide, we have a nice example which was developed by Anscombe in 1973. And in this study, they actually have 4 different cases or 4 different data and for all of them, actually, the linear regression is the same and the R-square values are the same. So although the data are different, as you can see, this is somehow a distributed linear regression-wise data with some errors, it seems. But this is a very curved polynomial can be fit very well on this, but we fit a linear regression curve or line. In here also, this is very good for linear regression, very constant, but there is one outlier. In here, for one constant value, we have many values. It seems like a statistical error exists here. But for all of them, when we apply the least squares fit for linear regression, we obtain the same equation, y equals 3 plus 0.5x, and also the coefficient of determination, r square, are the same for all. So 0.67, maybe we can say this is, because this is not close to 1, it looks a bad fit. Actually, it is true for this, for instance, but for this one, well, this is a good fit for this. There cannot be any better regression, actually, if we want to use regression in this. Similarly, for this one, this looks very good fit. Just outlier is a little bit bending it towards top, but other than it, it's very good. Also for this one, you can see there is one data here, and this one, a mean of this is actually passing through the line. So this looks very good as well. There cannot be any other option here. But for this one especially, a second order or third order curve can be better to be able to have a fit. But still, it has the same r square with this one. So should we say that this is also a good fit? Or should we say this is a bad fit? So that really depends. And that's why this example dramatically illustrates why developing plots are so valuable. So according to this study, we can see that along with the r-square value, check the plot as well. Plot the data, plot the curve that you actually fitted, then check if it really fits according to you or not. So we need to have that plotting evaluation, visual evaluation as well. We can implement the linear regression using the least square as a computer program, and you can see the pseudocode here for linear regression, and it's a regress function. As you can see, it has x data, y data, number of data, and some parameters here, and we are actually summing x's and y's and also having the mean values, and a1 is calculated by this formula, as you remember, and a0 is calculated by this. So we basically have all of these. Then after this, we will calculate st and sr, which are used for the r-square using these lines. Once we are done with this, we calculate the syx, and then we get the r-square value. So with this r-square value, we can have an evaluation of goodness of fit. Also, we need to add a plotting So we need to expand this program to include a plot of y versus x, showing both the data and the regression line, so that we can decide if the regression line is a good fit for the data. And the inclusion of the capability of plotting will greatly enhance the utility of the program in problem-solving contexts. So let's have an example to use this linear regression pseudocode or algorithm in MATLAB. MATLAB actually can be used easily to be able to write these algorithms. Let's see that in the next slide. In this slide, we have example 13.3, a linear regression example in MATLAB, and this is the parachutist example we used throughout the class. So we have the measured velocity, the calculated velocity by the mathematical model, or this is an analytical model. You can see here, this is the part B model. So we calculate V's for using this equation. In A, we have experimentally measured velocity. In B, we have the velocities from this model. It's called mathematical model. And in C, we have another model, but this is called empirical model. So this is basically a simplified version of this. This part is simplified, as you can see here. It only depends on T. So we want to evaluate the goodness of the data that we obtain from B and C, because the measured values are the correct values. And for different times, when we substitute these into here, we can calculate V's, and V's are here for analytical model. And for empirical model, these are here. And we want to apply regression to be able to check the accuracy of the calculated results in B and C based on the measured results in A. And we can do this by simply plotting a line of this with respect to this. So these will be x values, these will be y values. Also, these will be x and these will be y values. So we will have two data correlation to check these and these based on A. And if this line is a straight line, a 45-degree straight line, that means actually the model data is very good. And if not, it is bad actually. So for that, we need to plot the model calculated velocity versus the measured velocity. So for example, for B versus A, and also C versus A. Then we will use linear regression to fit a line for these data. If the model matches the data perfectly, then we will have, as we said, a 45-degree line. And this line will have a slope of 1, an intercept of 0, and r square should be 1 as well. So we will check the plots as well to understand if it is a good fit or not. And deviation from these values can be used as an indication of inadequacy of the model. So this is widely used to be able to understand if a data is very good in accuracy compared to a measured data or existing data, let's say. Let's check the result in the next slide. Here you can see the results of the regress function in MATLAB. So this regress function is the pseudocode that we showed in 2 slides before actually for the regression algorithm. And when you write it down to MATLAB and use it for fitting data, for first measured results versus analytical results and measured results versus empirical results. Use that data and have a least square formulation to fit. It's just a linear formulation, you can see. So if this is a very good 45-degree, that means we have a very good fit. But you can see the model has a little bit deviation. So this should be actually 0. This should be 1 for a perfect fit. But if it is deviating from those values, then the fit is getting bad. But still you can see this is nearly 0 actually, and this is nearly 1. So this looks very nice estimate, we can say. On the right hand side for empirical results, you can see the model again. The graph is this, and this value is very far away from 0 compared to this one especially. This is further away, and this one is close to 1, but it is further away from 1 compared to this one. So these results are closer to 1 and 0, 1 and 0. That's why this model, actually the analytical results, are better predictions of the measured results. So we can say that the analytical model is better than the empirical model in terms of accuracy. And also, if we compare the correlation coefficients, both of them match data with a coefficient of greater than 0.99. So this is not really a good indicator. And because both of them are have almost the same value and close to 1, so both of them looks good. But which one is better? Actually, these values show that. So this has to be close to 1, this has to be close to 0. This is a better model compared to this one, compared to experimental one. As we said, the slope and intercept give away the indication that this analytical model is a better model in terms of accuracy compared to the empirical model. So the correlation coefficient is not a good indicator here by itself. We need to check the intercept and slope as well as maybe the curves, but curves looks good as well. But you can see the deviations. These deviations are because, especially not that deviation, but being away from 45 degrees. So it has to start from 0.55 to 55 actually. Here almost there. So this is a better line. It has to be a 45-degree line for a good model in terms of accuracy. So you can give it a try by writing your own regression function in MATLAB and using these data and plotting these. See if you can get the same results. In MATLAB, we have also built-in functions for regression or polynomial fits using least squares. This polyfit function is built in MATLAB, and you can directly use this as an input like this, polyfit. X and Y are the vectors or one dimension, actually one column or one row vectors, and n is the number of data. So number of the degree of the polynomial actually. The degree of the polynomial function is n. For linear regression, it should be 1. And the polynomial function that it fits is this. Actually, it starts with only x to the power 0, just one coefficient, x to the power 1, x to the power 2, and the coefficients, summing them each other, gives the polynomial that we want to fit. Based on the degree, it only uses that number of polynomial terms. So if this is 1, it only uses these two. So Pn and Pn plus 1 will be calculated if this is 1. And so it returns a vector of P, this one, containing the polynomial coefficients. So for example, for n equals 1, it returns P1 and P2 values. And we can use this fit function and to be able to estimate some values for new inputs of x's using polyval function in MATLAB. And simply you use the P that you obtained here. These are the coefficients. It creates the linear regression, then inputs the new x's to be able to predict the y's. And you can check if x and y is suitable by plotting them as well. So in here, for the example, you can see we used actual linear regression for the example in the previous slide for analytical model and empirical model. And if we use polyfit for analytical model as well as empirical model, x's will be the same. These are the experimental data or measured data, and 1 is the linear regression. So we use this the same, n is 1. And PA will give the linear regression coefficients for the analytical model and results, let's say, and PE will give the linear regression equation coefficients for the empirical fit, let's say. And in here we obtained the same coefficients. You can see that we obtained in the previous slide. You can go back and check. They are the same. And here also for empirical model, we have the same coefficients as well. You can see that again, this is close. This has to be close to 0. This has to be close to 1. This is a better fit actually. Also, you can plot them by using this code, basically a figure plotting x and y, and also with polyval, we obtain new values from the linear regression and plot them as well in the limits of 555, as we showed in the previous slide. So you can see the plot is almost like 45-degree line, which is a good fit. And for the second data, we can fit as well. I mean, this is a little bit further away from being a 45-degree line. So this is actually the empirical data is not a very good prediction of the measured data here. So the analytical model gives better predictions of the measured data according to these results. So polyfit and polyval, these are very easy to use in MATLAB. You can directly use them for regression.